Hi everyone and welcome to the Barely Coding YouTube channel. I am your host Daniel Bark, and in this video we're going to take a look at AssemblyScript. And what is that? That is a language that tries to resemble the syntax of TypeScript with of course a few limitations, because what it compiles to is WebAssembly. So I think this could be the go-to language for JavaScript and TypeScript developers that want to write WebAssembly. We're going to implement a few functions, then we're going to verify these functions by writing some tests. After that we're going to run a benchmark, so we're going to implement the same functions in JavaScript and then compare the performance to see where we do gain some performance by using WebAssembly. We're going to see if we can identify some pitfalls, because there is a price to pay when you talk between the JavaScript and the WebAssembly modules. So let's jump into the code. Okay, so let's see what that init got us. We got a new dependency, which is the loader that can be used to import WebAssembly modules. We have some scripts, so AS build untouched, that will build the debug version. We have AS build optimized, that will build an optimized release version of our code. And if we run just npm run AS build, it will run both of them. We also have some tests, and those are located in tests index.js. So it's using the node library assert, which is a built-in library node. It imports the module. Here it tries the add function, so that tells me that there should be an add function in this file now. So here's the add function. So this is pre-compilation, so it says this is the entry file of the WebAssembly module. So we have just the add function. Here we have some config for TypeScript. It tells TypeScript that this is AssemblyScript, not regular TypeScript. So if we look now in the index.js, we see that it's using loader, which is the AssemblyScript loader. The path is build optimized. So this file will use the release files for now. And then it does a re-export. It takes the WASM module exports and places them on this file's exports, which means that we can import the WebAssembly modules from this file. So that's what this test file is doing. It's going up a level, importing in that folder, which would lead to this file. So here it's asserting, it's testing the WebAssembly add. 1 plus 2 should be 3. So now I should be able to do npm run tests. And it says okay. And I think that was correct. Yeah, it said okay. We can also do a console log my module dot add 2 and 2. Let's see if we get 4 outputted as well. Yeah, and we do. Okay, cool. So we have the build step working and we have the tests working. So now let's add another function here. Now we're going to create a factorial function. Take in a number again. We will return a number. This will be a recursive function. So we will return if I equals 0, then we return 1, else we return I times, we will call ourselves with I minus 1. So if 3 comes in here, then I is not 0. So then we will go to here with 3 times factorial of 2. Second time we will take 2 times factorial of 1. So what this will end up being will be 3 times 2 times 1 and so on. If I call this function with 3, I should get back a 6. So now we made some changes. So now let's do npm run AS build again. Seem to have gone okay. So now we can try factorial. We call it with 3 and we should expect that to be 6. And we can do it like this and say add is okay. Factorial is okay. Or we can do a console log Factorial my module.factorial and 3. Let's run the test. So add was okay, Factorial was returning 6 and okay. Great, so now we have 2 functions. So now let's start looking at how to benchmark this. So we'll do npm install benchmark and let's create a new file, call it benchmark.js, const benchmark equals require benchmark, and we need to import our WASM modules, so we'll do require this folder that will lead us to the index.js. Let's set up a suite here, run suite, we'll pass in the suite. So this means the test suite. We can console log that we started, running suite.name. And let's say suite on the cycle event. We'll set up a callback. We get in an event here. We'll just console log the event.target. Chain on another one here. Complete. Not sure we can have these as arrow functions because I'm going to use this to access the suite. This.filter for fastest. We map name 1. Let's start out with our add test. Add test. So we'll do function add JS. So this will be the JS version of add. A plus B. And the AssemblyScript version is wasm.add. So let's set up a new test. Test equals benchmark.suite. Call it just add. And now we run this test. So we do test add. We'll start with AssemblysScript. So we'll just add 10 to 20. And then another one for JavaScript. So now we can do run suite. We'll pass in our test. And all we need to do down here is call add test. Let's add the benchmark as a script in here. Benchmark. Let's try it out. Benchmark. Running add. Okay, I'm missing something here. Okay, I think it's this. Now it should work better. Let's go again. Now we should see some results. Okay, now it seems to be running. So we'll run many times through each of these test.adds. Okay, so now we got the result. So the assembly script was called 88 times and the JavaScript 84 times, and then averaged operations per second. We see that JavaScript was a lot faster. It was able to execute a lot of more operations per second. So we can see when this really simple function runs, then the cost of switching to AssemblyScript is a lot higher than what you gain from the actual speed. Okay, but the factorial function, in that one we can make the function run a lot longer. So I think that one should be quite interesting. So let's copy this add test. So we'll call this Factorial and this one we need to implement Factorial. Call it JS. So we have just one in parameter. So we do the same. We do return return I equals 0. If 1 equals 0, then we just return 1. Otherwise, we return I times Factorial JS with I minus 1. Okay, and let's fix these parameters here. We can run it. Let's run it with 20. And with this one, I want to split it up in 2 tests. So I'll call it Factorial small. And we'll do the same for large. Let's do 20 here, and for the small one, we'll just do 3. Test large, 20, and here we also do test large. Okay, and then we just call Factorial Test. We can skip add test for now. Let's run another benchmark. Okay, start with the small one. AssemblyScript is done. Okay, JavaScript came out ahead just a bit. So it's 27 million ops per sec versus 35 million ops per sec. So JavaScript won that one. If we look at the larger factorial, we can see that AssemblyScript was an even race in the small one. But for the large one, AssemblyScript was quite a lot faster. So AssemblyScript won this factorial one when we used a factorial of 20. So that's pretty cool. So there we could actually make some gain. But what I also want to try is what happens if you pass a large payload into AssemblyScript. Okay, let's create a new function. We'll call this one SquareArray. It takes an array, and this is an int 32 array, and it returns an int 32 array. So an array of the same size will go in and then come out, but squared. So the length is array.length. We'll allocate an array for the result. New int 32 array of length, and now let's start looping. So we'll do for let I equals 0, I smaller than length, I, and do plus I. So we'll take e from array I, result I is equal to e times e, and then we return result. We're now finished with the square array. Now we need to add some stuff here because we're passing an array between WebAssembly and JavaScript. So we're going to export some type IDs here, and you will see why in just a bit, but let's do int 32 array underscore ID. This is what we call the variable, and we'll use a function called ID of, and then int 32 array, like this. So this will give us the ID of that type. Okay, so now we have exported that type. So now let's go to where we import the WebAssembly module. So here we're actually going to create some glue code for this function. So we're going to create SquareArray here as well, where we just take in the WebAssembly version of SquareArray and we glue it together, and we export this version of SquareArray that is calling the WebAssembly SquareArray version. So here we get passed in the array. This is the array that comes from our JavaScript file. Destruct the SquareArray from the WASM module.exports. We can call it WASM SquareArray. But we also need some more things. We need our type, int 32 array ID is what we called it. Now we could do this, const result equals WASM SquareArray. So you might think that we could just do this. So you might think that this would work, but it won't. We have to first instantiate an array that is of the correct type. So we'll call this typed array. So we're going to create a typed array with the correct type. So we will import the function new array from here, and we'll also import the function getInt 32 array. So we can use this one to instantiate the array, and here is where we give it the type ID. So int 32 array ID, and then the array that comes from JavaScript land. This function takes the JavaScript array, and the type ID returns a typed array. We can then pass this typed array into the WASM SquareArray. But in order for this one to come back as a JavaScript array again, we need to wrap this in the getInt 32 array like this. This is the most complicated part of it, but here is where we get the array to match the WASM type, and here is where we take the WASM type and make it to match JavaScript land again. Now we need to add this SquareArray to our exports here. Cool. Let's compile our files. npm run as build. Okay. Let's write a test for this one. SquareArray. Okay. SquareArray. And this one we can do 1, 2, 3, 4. We expect that to be 1, 4, 9, 16. And then the strict equal should be deep strict equal. npm run test. Let's see if we need to do any more thing with the types. We get an error here. Let's see if we need to do this. New int 32 array. Now when I'm running it, it says operation requires compiling with export runtime. So let's add that to our AS config, to the release, export runtime true. Okay, let's compile it again. Okay, npm run test. Okay, it worked now. So let's see if we actually needed this type on this array, or if it's happy with just this for the test to pass. Okay, it's not happy with that. Let's leave it like that then. Cool, tests pass. We can square our array using WebAssembly. Now let's do the benchmark. So let's copy the Factorial one, take in an array, JS. So let's do the same. Let's copy this one. This one is SquareArray, SquareArray Test small is SquareArray small, SquareArray AssemblyScript, and SquareArray JavaScript. So here we'll do 1, 2, 3 because this is a small one. 1, 2, 3. Okay, let's copy the small test. Large. Large. Okay, now we only need to make these longer. Okay, remove the Factorial test and call SquareArray Test. npm run benchmark. Okay, so for the small one, JavaScript was a lot faster. So as we can see that the AssemblysScript had about the same performance in both, where JavaScript lost a bit of performance when the SquareArray was large. So let's create a really large array. So let's do new int 32 array of length 100. Let's fill it with ones and then just map val index val plus I times 0.01. And now let's try it with this large array instead. So now the test large will be of length 100. Okay, now the difference was a lot smaller. Let's see if we can make this 1000. Okay, so we have some interesting results here. The interesting thing here is that what we learned from the Factorial one is that if AssemblyScript would have been able to produce this array or have this array already in memory, it would crush JavaScript in the performance, like we see in the Factorial test. So in this example, we can see that there are lots of losses when we're passing this large array between JavaScript and WebAssembly. So I'm going to quickly type together the same test, but this array is generated on the AssemblyScript side, so we don't have to pass the big payload. Okay, so now I created it. In this version, we just pass in the length of the array that we want, so we don't have to pass a large payload between the JavaScript world and the WebAssembly world. So now let's see what performance we get. Let's call SquareArray Gen Test. Oops, let's not run all of them. So here we are doing it with 200 elements, and in the small test we're doing it with 20 elements. So as we can see, in the large test, AssemblyScript was over 2 times faster. And now we're running the small test. In the small test, it was still faster, but not by as much. So what we can conclude from this is that the size of the payload that we pass between JavaScript and WebAssembly matters a lot. So what we can learn from this is that The size of the payload that is being passed between JavaScript and WebAssembly matters a lot. But if we can have the data already on the WebAssembly side, and there are at least a few iterations that are going to be run, then WebAssembly will quickly regain the lost time of switching the contexts. This was super interesting. The code will be available on GitHub and you can check it out and try it yourself. Thank you so much for watching. If you like the content, then subscribe to the channel, share it with a friend, thumbs up the video, and I hope to see you in the next video.